Welcome to Chapter 1, also known as the first chapter. We are starting physical science by building the basic skills that we need to use for the rest of the course. First, we will talk about what science actually is and how scientists investigate questions. Then we will look at measurements, units, accuracy, and precision. And then finally, we will finish the chapter with graphing and how scientists organize data so that other people, me, can understand it. None of these ideas are limited to one unit. We will use them throughout everything that we study, whether that's matter, energy, motion, forces, waves, and anything else that happens in this year. So even though it's an introductory chapter, these skills are going to show up again and again. Welcome. Science. I hardly know him. What is science? Science is our method of studying the natural world. The key word here is method. Science is not just a collection of facts that somebody memorized. It is a way of asking questions, gathering evidence, testing ideas, and using that evidence to figure out how the natural world works. Science is usually divided into three major categories: life sciences, not this class, earth sciences, and physical sciences, this class. Life sciences focus on living things, like us. Earth science focuses on Earth and the systems connected to it, like space. Physical science is a category we will focus on in this class. As the image on the slide suggests, science can include things from DNA and microscopes to molecules and laboratory equipment. The subjects may look very different, but they all use evidence to study the natural world. You have a job in this class, and it's not just to learn the essential standards. And I want you to remember it throughout the year. Find the loophole. If the goal of science is to understand the natural world, then we should not simply accept the rule because somebody tells us it's true. We should ask a question about it. What conditions does the rule apply to? Can we think of an exception? What's the evidence that supports it? Is there a situation where it stops working? I'm going to tell you a secret in chemistry all the time. The image on the left is Jesse Pinkman, and I'm not going to finish it. But science becomes more useful when people test ideas instead of treating them as something that's untouchable. So when I give you a rule or a pattern, I want you to think of why it works and whether or not you can find a limit to that idea. This is a picture. You'll see many like them. Scientists explain the natural world by investigating it, and the one way we organize that process is the scientific method. I'm sure you've heard of it. If not, it's pretty cool. Look at the flowchart. We begin by asking a question. What is the question? That's the question. Then we do background research. The background research is this slide. And then we understand what is already known. From there, we construct a hypothesis. Why is he talking like this? In which we need a testable explanation or prediction. He's probably trying to teach me something. We test that hypothesis with an experiment, analyze the results, and draw a conclusion. You're watching the video, so I'm going to say you're the experiment. If the hypothesis is supported, we report the results. If it's false or only partially supported, that does not mean the experiment failed. The diagram sends us back to think, revise the idea, and try again. That loop is important. Science is not always a straight line from question to answer. It's usually not. Often the first result creates a better question, and investigation continues. Also, just to reiterate, we're reporting results if we're right or wrong, or else the next person who attempts it doesn't know if they should try the same thing we tried first. Science is about community. Question time. It's going to be hard for you to answer this, but that's what Wayground's for. If the scientific method depends on people reporting their results, what happens if somebody lies? Think about that. People are liars. People also tell the truth. There are two wolves in me. Science only works when evidence is being reported by trustworthy means. So if someone invents data or hides their results or reports something that does not actually happen, other scientists might waste time building new work on false information. And then the government might fund that research, and then we are wasting our money and time as a society on things that do not exist. One of the strengths of science is that the results have to be able to be checked. You can't just willy-nilly repeat an experiment and get different data, or else it conflicts with their original data. So we need to compare that, and we need to make sure we get similar results. That doesn't mean that we just ignore dishonesty, but it does give science a way to catch problems over time. And that's the rub. Sometimes it takes a long time. The larger point is that accurate and honest reporting is not optional. It is part of the scientific process. Don't be a liar. So we need to avoid kind of an obvious problem here. Personal bias. When we are doing an experiment, your personal opinion is irrelevant to what the data actually shows. You may really want a certain result, but that does not make it true. This nice little picture we got here with the scientist knocking out one of his petri dishes is a good example of how bias becomes a problem. If we only keep the evidence that we like and throw away the evidence we do not like, we will make the data biased or appearing to support anything we want. If you've ever asked somebody to prove it, and then they go and they pull up the first Google AI result to try to prove their point, you'll go, well, that's not what I'm talking about. And no one wins. Our job is to record what actually happens, and even when the result is unexpected. No one wants skewed data, and good science depends on treating all of the evidence consistently. Don't be a schmuck like that guy. Variables, I hardly know him. When we design an experiment, we need to take especially good care of tracking our variables. The control is the normal condition that we compare our experimental results to. The independent variable is the thing that we change, or I like to say independent means I change it. The dependent variable is the thing that we are measuring, so it's the thing that changes. And then the diagram on the left uses our plants as an example. The independent variable might be the liquid used to water the plant. The dependent variable could be the height or the health, if we have some way of checking that. On here, we're using the height. And then the image shows the controlled variables, which are things that we try to keep the same. Like it's the same type of plant, it's the same type of pot, and it's the same amount of liquid. A good experiment changes one main factor at a time so we can tell what's actually caused the result we observed. And that goes for any experiment you've ever read about, whether it's about people or plants or bacteria or earth settings. We have to keep everything consistent and change one variable at a time. Modeling, that guy's not a good model. Scientists also use models, not that kid though. A model helps us visualize an idea, event, or object so that we can understand it more easily. It's also a much easier way of showing it to other people. Sometimes a thing is too big, or too little, or too dangerous, too expensive, or simply impossible to directly observe. A model gives us a useful substitute. This picture shows the nice model volcano, and obviously a classroom volcano is not the same thing as a real volcano because that hurt. But it can represent part of the process on a much smaller and safer scale. Models can also be diagrams, simulations on a computer, equations, maps, or physical objects. By visualizing or testing on a smaller scale, we can develop ideas about how the real system may behave, generally. Just because you should remember every model is a simplified representation, it is not the real thing. We will have a lot of representations in this class on atoms. You can't see atoms, me either, but we can make representations, and there's a lot of different representations. Laws and theories. It's my favorite part of this chapter. Um, Most of the time, these two terms are confused. A theory is an explanation of things or events that is based on knowledge gained from observations and investigations. A scientific law is a statement that describes what happens in nature. The most useful distinction is that a law describes a pattern or relationship, while a theory helps explain why that pattern occurs. This nice graphic right here shows observations, hypotheses, theories, and laws in a simple stack diagram. For this class, focus on the definitions rather than treating the picture as a ladder where one idea automatically turns into the next. A theory doesn't become a law just because time passes. They do different jobs. They are both supported by evidence. One is the why, one is what it is, observably. Now we're moving on to section 2. This section is all about the numbers, measurements, units, and the way scientists communicate quantities, meaning an amount of things. These ideas will seem very simple, but they do matter a lot because measurement is only useful if we all understand exactly what and how something is measured. We will also connect measurement to the metric system because that's the real one. Temperature, accuracy, and precision. Numbers, I know them. In science, numbers work a little differently than they do in math. In a math problem, a number can sometimes stand on its own. In science, numbers usually have to have attached physical quantities. If I simply tell you the number is 7, a scientist would immediately ask, 7 what? 7 meters is a length, 7 seconds is a time, 7 grams is a mass, 7 degrees is a temperature, degrees of something. It's also circles. Those labels are not extra decoration. They're part of the measurement itself. This is a very nice picture of the bear. We don't know what the 7 means. What does the 7 represent? The bear ponders. He does not know. How long is it going to take? 4? Maybe 5? Days? Weeks? Could be 7. Years? Do labels matter? Not those kind of labels. Just because I tell you the label matters doesn't mean automatically that they do. So let's test this idea. We're going to play a game of telephone in class. This will be like after we watch this video, so you'll know. I'm gonna send information down the rows in 2 teams. Hopefully, we all know how cell phone works or the phone game, and I'm going to give you a lot of detail on one of the trials and a little bit of detail, and we'll see if we even remotely get to the same answer at the end. Communication, we'll find out, only works when the message that arrives is the same as the message that was sent. This is all about our measurements. A number without enough information is quite meaningless. SI, I hope you guys learned your Greek and Latin, because I didn't. To label measurements consistently, which is what we hope to do as scientists, we use the SI system, which stands for the International System of Units. The purpose is standardization. Scientists in different places need to be able to look at a measurement and understand the exact same thing. On this slide, we've got several units that we are going to be using in physical science. Length, very commonly, we will be measuring in centimeters and meters. Mass will be in kilograms. Time in seconds. Temperature will be in Kelvin. We'll talk about that one. And volume is in liters. Density is one that we'll talk about now, and that is a mass per volume. And only one common density unit is grams per cubic centimeter. The important idea is that every physical quantity has an appropriate unit. Once we agree on the unit system, measurements can be compared and communicated much more clearly so that we don't have to do a bunch of metric conversions just so we can all know exactly what the number represents. Ooh, all right. I hate to tell you guys, you're either going to learn these right away or we're going to be pulling some teeth. So believe with me here. The metric system is extremely useful because each unit can be modified by just changing the prefix. The prefix lets us describe something very small or very large without changing any string of zeros. The table on the left has a bunch of prefixes ranging from very, very large, like exa and peta, if you have worked with any kind of computer stuff. A petabyte would be the step above a terabyte. Uh, and then we go all the way down to like pico, femto, and atto. We don't use most of those prefixes, but the ones you'll see most often are from my good friend uh, King Henry died by drinking chocolate milk. You'll become quite acquainted with him, and that would be for kilo, uh, and for centi, and for milli, and the other base unit info. The key for all of this is that a prefix represents a power of 10. So every time we change a prefix, which is the same as changing the decimal point from the left to the right, we are going to change the unit name, but not change the physical quantity we are measuring. Get ready for a lot of fun practice with the SI system and metrics. All right, and also get used to this right here. This is our King Henry died by drinking chocolate milk moniker that I'll go through first. So let's make sure I've got my laser pointer out. All right, K for kilo. That's the king part. Henry died, base unit, by drinking chocolate milk. So if we take a test and you do not have this list with you, I want you to quickly be able to say King Henry died by drinking chocolate milk. You will write that down on your paper in a stair step, and guess what? You've just figured out how to do metric conversions. So more basically, if I am moving between my rungs, I'm changing by a power of 10. So if I convert to a smaller unit, the value becomes larger, so the decimal moves to the right. And if you convert to a larger unit, the value becomes smaller, so the decimal moves to the left. The number of places you move depends on how many rungs you travel, like on this ladder. We will practice this a lot in class, but the important idea is that metric conversion is based on consistent base 10 pattern rather than a bunch of collections of unrelated conversions, like if we did inches to feet or to yards. Temperature? What? I already know how to tell temperature. It's right there in Fahrenheit, the only one that matters. That's where you'd be wrong. See, in science, we usually measure in Celsius, and then we have to convert to Kelvin. But most of what we're going to be doing to start class is just going to be Celsius. Celsius is actually based off of uh, an important science thing called water. Water's pretty cool. Um, see, Fahrenheit's based off of freedom, but we're probably going to base it off of water for this class. So uh, I know you're all familiar with Celsius, like you know what it is. We will need to know how to convert between them, but I'm much more worried about you knowing what it represents. So we'll practice the conversion, but then after that, I'll just let you use a tool that I'll have out in the room. Water freezes at about 0 Celsius, right? But it also freezes at 273 Kelvin. That's pretty cool. Or around 32 Fahrenheit. Water boils at 373 Kelvin, 100 degrees Celsius, or 212 Fahrenheit. If you think about those numbers, 0 to 100 is a very easy scale to work with. Don't pay attention to absolute zero. We'll talk about that way later. So if it's anywhere between 0 and 100, you know we're working with liquid water. That scale will be useful for many different starting points, but they are at least all describing temperature. Temperature, again, for the conversions we're doing here, moving from Celsius to Kelvin is super easy. You take the Celsius number and you add 273. Try those two examples before I give you the answers. I'm not giving you the answers yet. First, 15 degrees Celsius. 15 plus 273 gives you 288 Kelvin. You'll notice I'm not saying degrees, by the way. Kelvin is not a degrees scale. It's a linear scale, so we don't use degrees. It's just Kelvin. Next, negative 20 plus 273 is 253 Kelvin. And you notice that Kelvin temperatures do not use a degree symbol. We're good? Good. It's a letter K, capital K for Kelvin. Ooh, here's a fun one. Are you good at darts? I'm not. Accuracy and precision sound like the same word. They're completely different words. They are measurements of the quality of a measurement, which seems like I just said nonsense words. You'll understand, hopefully, in a second. Accuracy is how close to a reported measurement is to the true or accepted value. Precision is how exact or repeatable the measurement is. We've got 4 targets on the bottom that show something different for each one. On the first target on the left, the shots are scattered everywhere. They're away from the center, so they have low accuracy. And since they're nowhere near each other, they also have low precision. On the second, the shots are tightly grouped, but they're super far away from the center, so the precision is high because they're grouped, but the accuracy is low because they're not at the bullseye, which is what we're shooting for. The third one, the shots are spread all around the center, so they're highly accurate because they're at the center, but they're not very precise because they're all around, they're not grouped up. And then on the fourth one, we are both highly accurate and highly precise because not only did we hit what we wanted to, we hit it each time. The last situation is what we want from our measurements. It won't always happen. Most of you are new to science, at least in the form where we're taking real measurements and doing real experiments. So don't feel bad if we're not highly accurate and precise, but there are things that we can control in our experimentation that will allow us to be more precise and more accurate than if we just did it willy-nilly. What is better, cat with mittens or cat without mittens? That's right, cats don't need mittens. So what matters more, accuracy or precision? The best answer is that we want both? Question mark. But it's a hard answer to get. Depends on who you ask. Also, if a measurement is precise but not accurate, we get nearly the same answer every time, but the answer can still be wrong. If a measurement is accurate on average but not precise, the individual results may be scattered and unreliable. This nice little Venn diagram treats accuracy and precision like overlapping categories, with the ideal measurement sitting in the overlap. It's close to the true value and can be reproduced consistently. In real experiments, we may not achieve perfection. We won't. We won't. They're not made for that. But thinking about both accuracy and precision will help us judge the quality of our data. Section 3. We are now moving on to section 3, which is all about graphing. A great scientist once said, I hate graphing. Not you. Once we collect our data, we need a way to organize it and communicate about it. A good graph can be a pattern obvious very quickly, while a poor graph can make good data almost impossible to understand. We're going to look at the major graph types and the basic rules for choosing and labeling them. Graphing is a visual display of information or data. That you should know that. Scientists use different kinds of graphs depending on what they are trying to show. In this section, we're going to focus on line graphs, bar graphs, circle graphs. Those are our major types. The image on this right, this little blurry doodad, is intentionally bad. You'll notice that the lines are crossing everywhere. They're different colored lines, which is fine, except they repeat. And they don't communicate anything really useful to us as a reader. I want you to think about this when you make your first graph and you submit it to me, because I might send you this back. It's a good reminder that the goal of a graph is not to simply put data on a page. The goal is to make data easier to understand. A graph should help the reader see a pattern, a comparison, or relationship more clearly than they could from your number set alone. Even though I also want to see the number set. What? Line graphs, they have lines, not the grid, but lines themselves. Not math lines either, because as you can see, these lines don't go infinitely long. Line graphs are useful when we want to show how a relationship between two variables changes over time, which means time is going to be on our lower axis. We'll talk about that. They also display multiple data sets from the same variables. The example on here shows that the average daily high and low temperatures for Monday through Friday. The x-axis, the bottom one, shows the day, and the y-axis, the tall one on the up and down, shows the temperature in degrees Fahrenheit. We don't use Fahrenheit, we use Celsius. Two different lines. Let us compare how high and low temperature patterns over the same period are different. Because the data points are connected, we can quickly see where the values rise, fall, or stay similar. When the order of the data matters, especially over time, that's an important bit, a line graph is often a good choice. Over time, we do the line. What's wrong with this picture? Take a look at this graph. What do you see? Is there anything wrong with it? You have to answer the screen like Dora or I can't move on. Do you see anything wrong with it? Yeah, it's bad. Let's start with the obvious. Uh, it's got months. They're not all labeled. It doesn't start at the beginning of the year. December is my favorite month, actually. December uh, doesn't continue properly. Also, what the heck are we measuring? It's over time. It's a line graph. Those are the only points I can make out of this. This is a good example of why labeling matters. A graph can only contain it can contain perfectly good data, which all data is, as long as it was collected properly. And it can still fail to communicate whatever the reader was trying to tell us. I think the reader here was telling us that this is a bad graph. They would not get the points on this graph and would be sent back to Go, and they would not collect $200. Variables. We talked about the variables. We need to talk about them again. Variables in line graphs are very important. Independent, the thing that I change, is going to be on the x-axis, which is the horizontal axis. It says day. When time is one of the variables, time will be the independent variable. It goes on the x-axis. The dependent variable is the thing that goes on the y-axis, which is the vertical axis. In the example on the left, the days of the week are on the x-axis. The number of Girl Scout cookies sold is on the y-axis. The number of cookies sold depends on the day being measured. Remembering independent on x, dependent on y, will make graph setup much easier throughout the course. Independent on x, dependent on y. Don't make me cry. I want to move on to the next slide. Bar graphs. So a horse walks into a bar graph. Bar graphs are designed to compare totals or amounts across categories. The important idea is that each bar is measuring the same quantity for a different category. In the example on the right, each bar represents a number of student birthdays in a particular month. The months are different categories, but every bar is measuring the same thing, which is the number of students. That makes the heights easy to compare. We can immediately see which months have more birthdays and which have fewer. Bar graphs work very well for separate categories where we want to be clear side-by-side comparisons rather than continuous change over time. If you're an August birthday, please stand up and exit the room. If you're in your own room, I'm sorry. I don't make the rules. All right, if you're wearing a red shirt, you're out for the day. Circle graphs are called pie graphs. Did you know pie is a type of dessert and also a type of food? Pets are not a type of food, unless pie graphs are used to show how a total is divided into percentages or parts. The entire circle represents the whole thing as an out of 100%, and each slice represents one category in that total. The example on this slide shows different types of pets. Dogs make up a large portion at about 40%, while the cats are at 25%. The remaining categories make up the smaller portions. Because the graph represents one complete total, all of the slices should add up to 100%. Circle graphs are useful when the main question is not how large the category is, but what fraction of the whole is each category represented. The final cautions about graphing. Make sure your labels are clear. Include units when the quantity has units. They almost always do. Choose a scale that makes sense and be careful if you have breaks in the scale because a strange or inconsistent scale can make your data look misleading. Your graph should make the information easier to understand, not harder. I'm the one judging that. The image on the right says, you've got this. And that's the point. You can read. But if you couldn't read that, that's cursive for got or to have. If you're not sure what a graph is showing up or how to set one up, ask for help. Not necessarily me, but you should ask for help. After you've asked other people for help, then you can ask me for help. I will help you. We did it! That ends chapter 1. We start with the basic idea of science and the scientific method, including variables, models, law, and theories. Then we looked at scientific measurement, units, temperature, accuracy, and precision. And finally, we worked through the major types of graphs, how to organize variables so data can communicate clearly. These are foundational skills, so they will continue to show up in almost every chapter after this one. We did it. You did it. We can now move on to the actual physical science content with a common set of tools that we all just unlocked. They're stone tools, but we have them. And we can ask questions, measure what happens, and communicate with the results. Let's get that iron set.